Hello and welcome back to Civil Engineering with Amir. This is Amir here with another video on the topic of shear force and bending moment. In the previous videos of this series, we've covered a variety of problems starting with simple cases like simply supported beams with point loads and gradually working our way through more complex load types and beam configurations including overhanging and cantilever beams with rectangular, triangular, and trapezoidal loads. In this video, we're going to analyze a more challenging beam with an internal hinge somewhere in the middle. If you've ever felt unsure about how to handle a beam like this, you're definitely not alone. A lot of students get stuck here, but don't worry, I'll walk you through it step by step. By the end of this video, you'll know exactly how to determine the support reactions, determine the shear force and bending moment equations throughout this beam, and then finally draw the corresponding shear force and bending moment diagrams using those equations. So stay with me until the end and let's break this down together. In this example, which is selected from Hibbeler's structural analysis, we have a propped cantilever beam with a total length of 9 meters. So at the left end or point A, we have a fixed support, and at the right end or point C, we have a roller support. At point B, or a distance 3 meters from the left end, we have an internal hinge. From point A to B, we have a uniformly distributed or rectangular load with a magnitude of 12 kN per meter. And from point B to point C, we have a uniformly varying or a triangular load with a maximum magnitude of 12 kN per meter at point B. And now the question wants us to determine the shear force and bending moment throughout the beam as a function of x, which is the distance from the left end or point A. Alright, let's start solving the question together. We're going to start solving the question by drawing the free body diagram of the beam. So if this is our beam, this is point A, this is point B, and this is point C. We have an internal hinge at this point B. At point A, we have a fixed support. So we have AY, we have AX, and we have MA. At point C, we have a roller support. So we only have CY. Our loading is like this. This is 3 meters. This one is 6 meters. And now the second step is writing the equations of equilibrium for this free body diagram and determining these 4 support reactions. And in order to do that, we should first substitute each of these 2 distributed loads with a single resultant force applied at their centroids. So for the rectangular load, we know the magnitude of our single resultant force will be the area under this rectangle. So 12 multiplied by 3 will give you a 36 kN single resultant force, which will be applied in the middle of this 3 meter distance, which is the centroid of this rectangle. So for this rectangular load, we have a 36 kN force applied at a distance 1.5 meters from the left end. And for this triangular load, the magnitude of the single resultant force will be the area under this triangle, or 12 multiplied by 6 divided by 2, which is also 36 kN. And that single resultant force will be applied at the centroid of this triangle, or the distance 6 divided by 3 from the larger end, so 2 meters from this point B. So this free body diagram here can be substituted by this one here. So again, we have a 36 kN point load applied at a distance 1.5 meters from point A, and we have a 36 kN point load applied at a distance 2 meters from point B. And now we can write the equations of equilibrium using this free body diagram. So in the x direction, the only force we have is AX, and if we write sigma Fx equal to 0 in this direction, we have AX plus 0 is equal to 0, and this will give us an AX equal to 0. In the y direction, we can write sigma Fy equal to 0, this direction. So AY minus 36 plus this CY is equal to 0. So AY plus CY will be equal to 72 kilonewton. If we take the moments around any point along the beam, for example this point A, we can say sigma MA equal to 0 this direction. So MA minus 36 multiplied by 1.5 minus 36 multiplied by 5 meters plus CY multiplied by 9 meters is equal to 0. So MA plus 9CY will be equal to 234 kilonewton meter. Now we have two equations and three unknowns, AY, CY, and MA. And that's exactly where things get a little bit complicated. We know if we cut the beam at any point along the beam, so if this is a beam and we cut the beam at any point, we're going to have an internal shear force, an internal bending moment, but we usually cut the beam at the third step, and we already determined our support reactions, and using those support reactions, we will be able to determine the shear force and bending moment at any point along the beam that we cut. But in these type of questions where we have an internal hinge, by cutting the beam exactly at the point where we have our internal hinge, we will be able to write an extra equation of equilibrium in addition to the ones that we already wrote using the free body diagram of our total beam. And then, by solving the system of three equations with three unknowns we have, we will be able to determine the three remaining support reactions. Now, if we cut the beam at this point B, we're going to have two cut segments. So, this will be our left cut segment. We have a downward shear force, which we call VB, and we have a counterclockwise moment, which we call MB, and our right cut segment will look like this. So we have an upward shear force and a clockwise moment. But the good thing here is, at the point where you have an internal hinge, your internal bending moment will be equal to 0. So this MB is equal to 0. And by analyzing any of these two free body diagrams and taking the moments around this point B, we will be able to write the additional equation we need to determine our support reactions. So for example, for the right cut segment, if we write sigma MB equal to 0 in this direction, we have MB, which we know is equal to 0 because we have an internal hinge at point B, plus 36 multiplied by 2 minus CY multiplied by 6 is equal to 0. And this will give us a CY equal to 12 kilonewton. And now if we put this 12 kilonewton in this equation, we have AY plus 12 is equal to 72. AY plus CY is equal to 72 kilonewton. And we know CY is equal to 12. So AY plus 12 is equal to 72 kilonewton. And this will give us an AY equal to 60 kilonewton. And using this equation, we have MA plus 9CY is equal to 234. We have the value for Cy, and we will be able to determine MA. So MA plus 9Cy is equal to 234 kilonewton meter. MA plus 9 multiplied by 12 is equal to 234. And this will give us an MA equal to 126 kilonewton meter. So by writing the equation of equilibrium for the right cut segment and taking the moments around this point B where the internal hinge is, using the fact that the internal moment at the hinge is equal to 0, we were able to determine Cy, and by putting Cy in those two other equations that we determined by writing the equations of equilibrium for our entire beam, we were able to determine AY and MA. We could also write the equations of equilibrium and take the moments around point B for the left cut segment. So in that case, we can write sigma MA equal to 0 in this direction. We have MA minus AY multiplied by 3 plus 36 multiplied by 1.5 plus MB is equal to 0. And again, we know MB is equal to 0 because the beam can rotate at this point B, and there's no resistance against rotation or bending at the point that we have an internal hinge. So MA minus 3AY will be equal to negative 54 kilonewton meter. So again, we have one equation here, two equations, three equations, and 1, 2, 3 unknowns. And by solving this system of three equations, three unknowns, we will be able to determine AY, CY, and MA. And the values you get for those three support reactions will be exactly the same as the ones that we determined by writing the equation of equilibrium using the right cut segment. So again, when you have an internal hinge along the beam, you can cut the beam exactly at the point where you have your internal hinge. You will have two cut segments when you cut the beam, and by taking the moments around the point where you have your internal hinge, and using the fact that your internal moment at that point is equal to 0, you will be able to write an additional equation, and using that additional equation and the other equations of equilibrium you wrote for your entire beam, you will be able to determine your support reactions by solving a system of n equations and unknowns. Alright, now that we have all our support reactions, we can substitute this free body diagram with this one here. So AY is equal to 60, MA is equal to 126, and CY is equal to 12. And now, in the third step, we should cut the beam at different sections and draw the free body diagrams for each segment of each cut section. So our first cut section will be somewhere between point A and B, or X between 0 to 3. So we can cut the beam like this. And our second cut section will be somewhere between point B and C, or X between 3 to 9. So the second cut section will look something like this. And for each of these two cut sections, we're going to have two cut segments. So for the first cut section, or X between 0 to 3, our left cut segment will look like this. So the length of our cut segment is equal to X. We have a downward shear force, which we call V1X, and we have a counterclockwise moment, which we call M1X, and our right cut segment will look like this. So the total length of our beam is 9 meters. The left cut segment had a length of X, so the right cut segment will be 9 minus X. 9 minus x minus 6 will be the length of this piece. So this is 3 minus x. We have an upward shear force, or V1x, and we have a clockwise moment, or M1x. For the second cut section, or x between 3 to 9, our left cut segment will look like this. So we cut the beam at a distance x from the left end. X minus 3 will be the length of this piece. We have a downward shear force, which we call V2x, and we have a counterclockwise moment, which we call M2x, and our right cut segment will look like this. So again, the total length of the beam was 9 meters. The length of the left cut segment was x. So the length of the right cut segment will be the total length, or 9 minus x. So this will be 9 minus x. We have an upward shear force, or V2x, and we have a clockwise moment, or M2x. And now in the next step, for each cut section, we have to choose one of the two cut segments and write the equations of equilibrium for that cut segment and determine the corresponding V and M. So for the first cut section, or x between 0 to 3, if we write the equations of equilibrium for the left cut segment, we will be able to determine V1 and M1, or we can write the equations of equilibrium for the right cut segment and determine V1 and M1. And these V1 and M1 will be exactly the same as these V1 and M1. And similarly, for the second cut section, or x between 3 to 9, we can either write the equations of equilibrium for the left cut segment and determine V2 and M2, or we can write the equations of equilibrium for the right cut segment and determine V2 and M2. For the first cut section, I'm going to choose the left cut segment because it seems to be easier to analyze on this one. Here we have a rectangular load, but here we have a small rectangular load and a triangular load. So I'm going to choose this one, but if you want, you can write the equations of equilibrium for this one. And for the second cut section, I'm going to choose the right cut segment, because here we have a triangular load, but on the left cut segment, we have a rectangular load and a trapezoidal load. So this one seems to be easier to analyze. So I'm just going to copy the ones that I choose to analyze and move them here. Okay, so for this cut segment, we have to substitute this rectangular load with a single resultant force. So the magnitude of our single resultant force will be the area under this rectangle, or 12 multiplied by x. And that single resultant force will be applied at the centroid of this rectangle, or right in the middle at a distance x divided by 2 from each end. So this free body diagram can be substituted by this one here. So I'm just going to remove this one and move this here. Now in the y direction, if we write sigma Fy equal to 0, in this direction, we have 60 minus 12x minus V1x equal to 0. This will give us a V1x equal to negative 12x plus 60. So from x between 0 to 3, our shear force can be determined using this function. If we take the moments around this point O, we can say sigma MO is equal to 0 this direction. So 126 minus 60 multiplied by x plus 12x multiplied by x divided by 2 plus m1x is equal to 0. And this will give us an m1x equal to negative 6 x to the power of 2 plus 60x minus 126. So from x between 0 to 3, our bending moment can be determined using this function. And now by doing the same process, we will be able to determine V2 and M2. So we have to replace this triangular load with a single resultant force. If this is our total beam, our total triangular load looks like this, and this maximum magnitude is 12 kilonewton per meter. Now, we know for this free body diagram, the magnitude of our single resultant force will be the area under this triangle, or 9 minus x multiplied by this height here divided by 2. So if we call this height wx, this is also wx, and we know the slope of this small triangle here is equal to the slope of this total triangle. So wx divided by 9 minus x is equal to 12 divided by 6. So wx will be equal to 2 multiplied by 9 minus x. So the area under this triangle, or the magnitude of our single resultant force, will be 9 minus x multiplied by wx divided by 2, or 9 minus x multiplied by wx, which is 2 multiplied by 9 minus x divided by 2, or 9 minus x in the power of 2. And we know that our single resultant force, which has this magnitude, will be applied at a distance 1/3 of this total length, or 9 minus x divided by 3 from the larger end. So this free body diagram can be substituted by this one here. So we have a single resultant force with a magnitude of 9 minus x in the power of 2, and it is applied at a distance 9 minus x divided by 3 from the larger end. So I'm just going to remove these and move this one here. Now, for this free body diagram, if we write sigma Fy equal to 0 in this direction, we have V2x minus 9 minus x in the power of 2 plus 12 is equal to 0. So V2x will be equal to 9 minus x in the power of 2 minus 12, or x in the power of 2 minus 18x plus 69. So V2x is equal to x in the power of 2 minus 18x plus 69. So for x between 3 to 9, we can determine our shear force using this quadratic function. And for the bending moment, if we take the moments around this point O, we can say sigma MO is equal to 0 in this direction. So M2x plus 9 minus x in the power of 2 multiplied by 9 minus x divided by 3 minus 12 multiplied by 9 minus x is equal to 0. So M2x will be equal to negative 9 minus x in the power of 3 divided by 3 plus 12 multiplied by 9 minus x. And now if we expand this function, we will get an M2 equal to x in the power of 3 divided by 3 minus 9 multiplied by x in the power of 2 plus 69x minus 135. So our M2x will be equal to, so for x between 3 to 9, We can determine our bending moment using this cubic function here. And now we can summarize our result using these functions here. All right, now let's draw the shear force and bending moment diagrams using these functions. Okay, so for the shear force, at x equal to 0 or point A, we have a positive support reaction equal to 60 kilonewton. So we have to go up. And this is 60. From point A to B, where x between 0 to 3, our shear force is a linear function. And it will look something like this. At point B, where x equal to 3, there's no point load, so there won't be any jump. And from point B to C, or x between 3 to 9, our shear force is this quadratic function, which will look something like this. And this is negative 12 here. And finally, at point C, we have a positive support reaction equal to 12 kilonewton. So negative 12 plus positive 12 will bring us back to shear force equal to 0. So we have to go up. And you can see that somewhere between point B and C, or x between 3 to 9, your shear force is equal to 0. So if you put this function equal to 0, you will be able to determine this x here, which is approximately equal to 5.54 meters. So this x here is approximately equal to 5.54. Now for the bending moment, at x equal to 0 or point A, we have a counterclockwise or negative support reaction with a magnitude of 126. So we have to go down. This is negative 126. From point A to B, this is our function for the bending moment. So we have a quadratic function, which will look something like this. At point B, where x equal to 3, we have an internal hinge. So the moment will be equal to 0. This is m equal to 0. From point B to C, where x between 3 to 9, we have a triangular load, and the moment is a cubic function. And the moment diagram will look something like this. And at x equal to 9, or point C, we don't have any concentrated couple moment, so there won't be any jump in our bending moment diagram at this point. So the moment will be equal to 0 at x equal to 9. You can also see that we have an extreme point between 3 to 9. So if we take the derivative of this function and put it equal to 0 for x between 3 to 9, we will see that at x approximately equal to 5.54, we have a maximum in our bending moment. So this is where your maximum happens, and it's 5.54, which is the same value as this x here, where we had a shear force equal to 0. And now, if we put this x in this equation, we will get a bending moment approximately equal to 27.72 kilonewton meter. So this is 2771. So these are the shear force and bending moment diagrams for this propped cantilever beam with an internal hinge at point B where x equal to 3. And you can see that at this point, your bending moment is equal to 0. Now, before I show you the diagrams I plotted using MATLAB, here's a question for you. Right now, our internal hinge is located at point B or at the distance 3 meters from the left end. And based on this configuration, we determined our maximum magnitude of bending moment to be equal to 126 kilonewton meter. Now, if we keep the same loadings and the same configuration for our end supports, but move this internal hinge 1 meter to the left or 1 meter to the right, so everything's the same except for the location of this internal hinge, what do you think will happen to this maximum bending moment magnitude? Or in which case you think you'll get a larger value for this maximum magnitude? Left or right? Write your answers in the comment section. Alright, now let's see how our shear force and bending moment diagrams will look like in MATLAB. So again, from point A to point B, we have a rectangular load, our shear force is linear, and our bending moment is quadratic. From point B to point C, we have a triangular load, our shear force is quadratic, and our bending moment is cubic. And this is how your shear force diagram will look like in MATLAB. And this one's how your bending moment diagram will look like. Alright, that's it. Thanks for watching this video. I hope you found it helpful and informative. If you like this video, please don't forget to hit the like button. If you have any comments, suggestions, or feedback, feel free to write for us in the comment section. And don't forget to think about the question I asked at the end of the video and write your answers in the comment section. And finally, if you haven't subscribed to the channel, please support us by hitting the subscribe button. Thanks again, and see you in the next videos.